Good afternoon, PreCal students. Hope everybody's had an awesome day today. Again, I have had to record this lesson, but hopefully it'll be okay. Again, I'll apologize in advance. Again, I don't have my Apple Pencil with me, so any writings I do on the screen are going to be a little bit blurry and a little bit terrible, I have to say. But I hope you did okay in the lesson yesterday. We're going to continue the concept here talking about polar form. Now, we talked about the polar coordinate system and the complex graph that with the x-axis being the real numbers and the y-axis being the imaginary numbers. So we're going to kind of continue this topic today and really just more conversions. This form right here that I have is called it's like the polar form. The r and the theta are the polar graph related to the complex number and the modulus of the argument, respectively. So if you think about this, guys, I'll make it very easy for you. Think of just the normal Cartesian plane. And whenever we had a coordinate, the x was always first and the y was always second. So it kind of parallels this. Again, if I were to draw this out, it's a little bit different though because the r is the actual modulus. So it's not like we count over 3 here and up 4 here or whatever. It's a little bit different. The modulus is actually the hypotenuse. So it's a little bit different than just the Cartesian plane, but it has the same idea. To be honest with you, it's more like the polar form that we've talked about last chapter with the graphing of the limicons and things like that, where r, whatever it told us r would be the modulus, the length of the hypotenuse, and then the argument would be theta. Again, we always draw that from the x-axis to the modulus. So again, I'll give you an easy one here. If I told you that the polar graph, and it gave you the polar coordinates here of, I don't know, 2 and 150 degrees. Well, the 2 is the length of the hypotenuse. It says 150, so hopefully y'all understand that's in the second quadrant, because here to here is 90, all the way around is 180. So it's bigger than 90, less than 180. And then I always draw my argument down to the x-axis. So this one's a little bit tricky. You got to be careful. From here to here is 150. So the argument would measure 30, but then the hypotenuse of this would be 2. The modulus would be 2. So that's the form that we're talking about, okay? So here's a better picture. Again, you notice all the pieces. Here you have the r, and then again, you have the r here, and theta is listed here as well. So that gives us the idea of what that's talking about. Okay, also gives us the formula for the modulus. We already know this. It gives it in terms of r here instead of the complex number. But again, it's simply the square root of x squared plus y squared. Don't get confused. This is nothing more than the Pythagorean theorem. If I can get it up here again, let's try it one more time. Nothing more than this is r squared equals x squared plus y squared. C squared equals a squared plus b squared. Same concept. They just take the square root of both sides, and that's where they get the formula there. Also, we know this as well. You could set up the tangent of theta is equal to y over x, and then they just take the inverse of both sides. So they get theta equals the inverse of tangent of y over x. So again, we've already talked about these. They're just putting them in complete perspective of x and y instead of the a and b. But it's the same concept, very similar. X is equal to r cosine. Again, if you set up, if you cross multiplied or if you solve for x here, it's the best way to look at it. We would solve that x is actually equal to r cosine of theta. And that also, we could use some trigonometry to figure out that y is going to be equal to r sine of theta. So don't get confused with that. It's nothing more than setting up your trigonometric functions, your ratios, and then cross multiplying and solving for x and r. So that's a pretty important feature, and we're going to see something else right now. Let's change it to a complex number, and you'll see again, we already have this formula written down, the equation for the modulus. We already have this equation written down. And so here, if we substitute our letter b and a instead of saying y and x, excuse me, we would set up this equation. A is equal to r cosine of theta and B is equal to r sine of theta. So this is nothing different than what we looked at on the previous slide. The only difference, instead of saying x and y, it says a and b. Because over here, this would be the x, which we replace with a, and b would be the y, and we just substitute the y for b. Again, why do we do that? Because now notice we're writing it in terms of a complex number. So it's the same exact concept, it's just substituting a and b in the place of x and y. Now this leads us to a very important concept. When we have a complex number, a plus bi, that is actually going to be equal to, because we just had it on the previous slide, what did a equal? A equaled r cosine of theta. What did b equal? B equaled r sine of theta. So it's just basic substitution here, guys. Don't get confused with that. And what they do next is they just factor out the r, because they both have r in them. Again, let me help you out understand this. This on the previous slide was equal to this. B is equal to r sine of theta, so it's just substitution. And then what they did is they both have r in them, so they factor out the r, and that's where they get this equation, or this expression I should say right there. That's actually very important, because that is actually written as r cis of theta. This is what the polar coordinate system actually equals. So it's very important to have these things written down. Oh, I just got away from it again. It's extremely important to have these two concepts written down on your formula card. Those are equal to each other. Now, it's not super difficult, but if you ever are asked to write something in polar coordinates or polar form, this is polar form, r cis of theta. And the a plus bi, we've already talked about this. This is complex form, sometimes referred to as rectangular form. So you got to make sure you know those, because you're going to be asked to convert from one to the other. And that's really what this concept, this lesson is all about. All right, so let's take a look at example 1. Change 2 plus 2 square roots of 3i to polar form. Now again, the textbook leaves a lot of vital information out. I'll do my best to explain it and make sure y'all understand it. So we're going to go ahead and convert this to polar form. Now what they do is they go ahead and calculate what the modulus is equal to. Don't forget something. All of this is based on graphing. So this is the A and this is the B. So if I wanted to graph A is 2 and Y is, or the imaginary number is 2 square roots of 3, I'm just going to estimate it to be right there. I could draw that to the origin, draw that to the x-axis. This measures 2. This measures 2 square roots of 3. So to solve for r, they just use the Pythagorean theorem. Okay, so don't let this be confusing. And then you're also going to have to solve for theta. So that's the process at which they do. So they go through all this, and they continue on solving this by substituting all the pieces in. They get 16, so r is apparently 4. Then they use your theta formula you have written down. Again, don't get confused. It's really just this piece right here. You have the adjacent and you have the opposite, so that's going to be tangent. So tangent of 2 square roots of 3 over 2. You plug all that in your calculator. Here they display it here for you, and you get that it's equal to pi over 3. So writing this in polar form, r was equal to 4, theta was equal to pi over 3. You're going to write that as the proper form, which is polar form. And this is where r cosine of theta plus I sine of theta comes in. It's very important. Now, again, I don't like how they assume this here. Pi over 3 is one we had to have memorized. So again, you got to memorize these key ones, which were pi over 4, pi over 6, pi over 3. Those were the main ones we have to memorize. Of course, you already know pi over 2, 90 degrees, and pi, and 3 pi over 2, and 2 pi. Y'all know all those already. But the pi over 3, the pi over 4, and the pi over 6 are very important, because I would recommend to actually think of it in terms of that. This is really 60 degrees, and this is also 60 degrees. If you'll do that, it makes a little bit of sense of what they're about to do. because again, they tend to skip some steps, but that's just 60 degrees. So literally, since it's the same, I can now rewrite this and finalize my answer and write it as 4 CIS of pi over 3. Again, because this piece right here is CIS, okay? That's all you had to do. You just graphed it out. If you'd like to graph it out, you can to see exactly how it works. That's perfectly fine. Or you could just use the formulas that you have written down for the modulus and also for the argument. Okay, so this one is a little bit different. It says this is the polar form. We need to convert it to rectangular form. So we hopefully remember that the cosine of pi over 6 plus 1/2 I sine of pi over 6 could be rewritten in terms of, you could factor out the 1/2. Some students prefer to do that. Like they literally would say 1/2, factor that out, and they would say times the cosine of pi over 6. Again, I'm sorry about the sloppiness of the writing. Plus I sine of, I'm running out of room, I sine of pi over 6. And y'all would understand that that really is the same thing as the CIS. Now, the reason I don't go to CIS is because that's polar form. I need to convert it to rectangular form. So you can see what they do here. Maybe you can see what they do here. They rewrite this in terms of trigonometry. They graph it out, and again, they leave out this very important step that I think the textbook assumes you guys already know this. They literally draw this out. Pi over 6, again, is equivalent to 30 degrees. It's in the first quadrant, so this is going to be 30 degrees. So it's a 30, 60, 90 right triangle. So this opposite of 30 is 1, opposite of 60 is square root of 3, and the hypotenuse is 2. So they rewrite cosine of this as the square root of 3 over 2, the adjacent over the hypotenuse. The same thing with sine of pi over 6. Sine of pi over 6 is opposite over adjacent. So again, opposite is the 1, opposite over hypotenuse. Opposite is 1, and the hypotenuse is 2. So that's how they write all that. Again, they assume you know that and you'll have it memorized, but most of you probably don't, which is fine. You're just going to have to practice this a little bit more before you can get a more comfortable working with that. Here again, change 3 CIS of pi over 4 to rectangular form. So this is similar to the last problem we just had on the screen. The only difference is it puts it in CIS. So your first step is to get rid of the CIS, and you have to remember, you'll have to have this written down, and you probably need to memorize it at some point. CIS is equal to, or stands for, I can't draw equal signs here. It's equal to cosine of theta plus I sine of theta. You have to memorize that, or at least have it written down and know what it stands for. So your first step is to rewrite CIS of 3 pi over 4 in terms of cosine of theta plus I sine of theta. So that's the very first thing that's done here. They rewrite this, they go ahead and take that 3 out, and they have 3 times the quantity cosine of 3 pi over 4 plus I sine 3 pi over 4. Again, the text assumes you know a lot here, and they go ahead and rewrite things, but they're wanting you to evaluate where is 3 pi over 4. So again, here's where they kind of make a bad assumption. Assume that you guys know exactly where this is going to be. So let me, let's see here. So I'll try to sketch it up here for us. All right, let me erase some of this so I can make some room here. All right, so if we were to draw this out, 3 pi over 4, again, if you want to think of it in degrees, that may help you. 3 pi over 4, and convert that to degrees. 3 pi over 4, convert it to degrees. That's going to be pi down here and 180 up here. So the pi's will cancel. This will give me 50. So 3 times 50 is 150. So we need to draw this triangle in the second quadrant. Okay? And then from here, the 0 angle, all the way to the modulus, also called the resultant, is 150 degrees. So once again, that's 150 degrees. So this angle right here is going to be 30 degrees. Let's see here. I'm questioning my work here. Let me check something real quick. Let's see here. Yep, I'm glad I questioned my work, because it's not 50, it's 45. So that's going to give me 3 times 45, which is 135. So I need to subtract that from 180. And yeah, I get 45. So I'm glad I recalculated that. Sorry about that, guys. The resultant is still there. I still need to know that from the zero angle to that resultant, or the modulus again, is 135, which my related angle, or the argument, whatever you want to call it, it's often called the argument, is going to be 45 degrees. So this is a 45-45 right triangle. 1, 1, square root of 2. So when it asks for the cosine of that, the cosine is adjacent. But be careful here. The adjacent is -1. You'll see that down there? That's -1, and this was +1. So I would literally say that's -1 over square root of 2. So what they do is, again, so you can see how much assumption they make here. They rationalize this. Square root of 2 over square root of 2, which is going to give me negative square root of 2 over 2. And you can see that matches up with what they have there on the slide. So you do have to do a little bit, again, nothing more than trigonometry here in order to figure out your proper ratios, in order to figure out what that particular angle is equal to. And then sine, I need to find the sine. The sine would be opposite over hypotenuse. So they do the same thing. 1 over the square root of 2. They rationalize that, and they get the square root of 2 over 2. So again, sorry they assume so much there, but that's actually how you need to do it. I'd recommend you to draw it out just like I've done, put it in the right quadrant, figure out what the ratio is going to be. And for now, they're always going to give you triangles that are special triangles. One you already know. Again, either 30, 60, 90 or 45, 45. So then they simplify that, they distribute out the 3, and they get their answer. And this is the answer. I just had it up here. That was your final answer. This right here will be your final answer. Again, that's rectangular form. CIS is always polar form. Okay, so we'll do one more example here, and then I'll let you get started on your homework. We got to change the -1 minus 4i to polar form. So the first thing I'd recommend to do is actually plot this out so you can see where it's at. So you plot it out, and again, the textbook assumes too much in my opinion here. Hopefully y'all understand that this can make a triangle, and that the height of the triangle is 4, and the base of the triangle is 1. So again, make sure you can do that, because now I have to find r, and now you can figure out how you find r, either using the modulus formula that you have written down, or using the Pythagorean theorem. But me showing you this triangle hopefully allows you to see how you could use the Pythagorean theorem. Because again, the base is 1, the height is 4. They are both negative, but remember, when you use the Pythagorean theorem, you're squaring a and b, so the negatives will go away. So you do that, use the Pythagorean theorem, and you're going to end up getting r, which in this case is going to give you the square root of 17. Again, just use the Pythagorean theorem or use the modulus formula. Either one will work. Then I need to find theta. Again, I need to draw this out. I want theta all the way around. But how do they get 4.4 radians? Well, that's a great question. Again, they just kind of assume you know. Well, first we need to use trigonometry. And I don't have my pencil, so this is going to be a little bit more difficult to do. I need to figure out what theta is, what the actual related angle is. It would be this angle right here that I'm kind of emphasizing. All right, so I need to figure out that angle. So I'd have to use trigonometry again. I'm going to use my formula. The tangent of theta is going to be equal to opposite. Opposite of theta is the 4, or -4. And the adjacent is -1. So on your calculators, you guys understand you're going to have to hit your inverse button. So I'll do that real fast on my calculator. The inverse tangent of 4, let's see here, mine's not working really well here. Here we go, let me try this. 4 inverse tangent, I got 75.96. So I got theta to be 75.96. Hopefully that's what you got. So what this is saying, guys, is, and again, my picture's getting really messy here. The black angle that I have, I'll use a laser here. The black angle I have right here is equal to 75.96. But remember, when I write it in the polar form, I have to write it all the way around. So again, I need to start here and go all the way around to the resultant, or the hypotenuse, or the modulus. Again, it's all the same. So I start here at 0 degrees, I go all the way around to here is 180, and then I need to add on the length of theta, or the measure of theta, which we just said was 75.96. So I need to say 79.56 plus 180. And when I do that, my calculator displayed 255.96 degrees. So that's what I got. So literally that is what this angle here, theta, plus the 180 will give you, 255.96. So you may still be asking the question, where do they get the 4.47 from? Well, it's as easy as converting this number into radians. So 180 has to be in the bottom, pi will be on the top, and when you punch that in on your calculator, literally 255.96 times 3.14, and then divide that by 180, my calculator displays 4.465, which does round up to 4.47. So they put it in radian form, and that's perfectly fine, but that's exactly how it would be written to convert it into that form. So again, really all you're doing here, guys, is using trigonometry. You're plotting some points on the complex plane, and then you're using some trigonometry, finding theta, and finding all that information and rewriting it in the form. And that's all there is to it. So the square root of 17 CIS of 4.47 would be the answer. If you leave the square root of 17 and you put it in a decimal, that's acceptable as well. So I won't deduct for that, but that's how that works, guys. Again, not too bad. Finding the product or quotient of complex numbers in polar form is relatively easy. Here's the formula here that's written. It's not super hard. It looks hard. It's basically saying I'm looking for the inverse of a function. So what they do is they actually factor out the r's, the resultants here. And you can see this. They literally just factor the r sub 1 and r sub 2 out. And then you add the two angles together. And that's going to give you the product, or in this case it's the product because it's being multiplied. So you can basically just factor it out and then go from there. That's kind of what this is talking about. If you divide them, notice you divide two complex polar forms, I should say. You have R1 CIS of pi over theta of 1 divided by r sub 2, say CIS or cis of theta over 2. You simply divide the radii, or also the modulus, the hypotenuse there. CIS, since you're dividing these arguments, you actually subtract them. Just like when we multiply them, we add to them. When you divide arguments, you actually subtract the two. And that's a simple way of finding the product and the quotient form. It's a lot easier doing this than graphing out the two triangles. You can actually graph out the two triangles on the complex plane, find them all, add your thetas together, add your resultants together. It's just a little bit faster to do this method right here. So make sure you have those written down. So here's an example. Find the product of these two polar coordinates, or polar form. So literally what we do is we apply our formula. Since you're multiplying them, I know I'm multiplying it because it says product, you simply apply the r's, which are 5 and 3 here, and you add the angles together, and here you're going to end up with 15 CIS of 5 pi over 12. Super simple if you have those formulas written down and can comprehend them. If I were dividing those, I would simply divide the two resultants, the r's, and then subtract the arguments. Here's an example. This says the quotient, so I'm dividing them. So I simply divide the 5 into 3, and I say CIS of pi over 4 minus pi over 6. Punch that in my calculator, just fractions, 1/4 minus 1/6, and I get 1/12, so that's pi over 12. So that's how that works, guys. Not too difficult. Make sure you have those formulas written down, and you should be good to go. Again, your substitute has the assignment for you, so make sure you get that completed. It'll give you some good practice, and when I return tomorrow, we'll be able to answer. I'll be able to answer any questions that you may have, and we'll get caught up on these 2 lessons. But I hope you have a fantastic day, and I hope you do well on the homework tonight.